Dynamic geometry software can transform the teaching of many mathematical concepts. Maths expert Carol Knights.
One of the great things about dynamic geometry software is that it's geometry, but it is dynamic. It's exactly what it says. You can set models up on the screen, move them around, change things around, and you can see the things that change and the things that stay the same. For instance, one of the most basic things is looking at angles in a triangle. We can see as we move any point at all the angles change. Move aside, and again they all change. What I can then do is add the three together. And we can see there that the total of the three angles is 180 degrees.
And this is something pupils can set up and explore for themselves.
Measure, calculate, add that 180 degrees. Always 180.
How would they have done this task without the software?
You'd have to
cut out one.
You'd have to keep drawing it, and draw another picture of it, and draw another picture of it.
While it's
and it get really annoying. But this makes us better. It's really good.
This is really good for the pupils because if you try and get pupils to draw the triangle out, measure the angles and then add them together, 9 times out of 10 they won't measure the angles accurately anyway, so they'll have a triangle where the angles add up to 181 degrees or 178 degrees. And if you're trying to convince Year 7s that the angles in a triangle add up to 180 degrees, there it is.
I'd like a volunteer, please. Thank you, Chloe. Would you like to come and show us?
This can also be demonstrated on the classroom whiteboard.
OK, watch the numbers as she's moving the blue triangle. Have a look to see what's happening to the angles.
Dynamic geometry software can also be used to illustrate mathematical proofs, like the sum of the angles in a triangle.
First you need to construct a parallel line, which we can just do from the menu there, and create the angle so we can see it in colour. We have the red, yellow and blue angles in the triangle, and then we have the red, yellow and blue angles on the straight line there, showing that the angles in a triangle add up to 180 degrees. The good thing about this is that it's not got numbers attached to it, it's got colours attached to it, and pupils often are far more ready to accept things almost in colour than they are with numbers. With numbers it would turn it into a demonstration rather than a proof, but the colours just bring it to life. With dynamic geometry software, it's not just geometry that you can do with it. One really good example is this dynamic number line. What I do with this is ask the pupils what they notice about the way A and N move. And with this first one, pupils will say that they're moving together. So A is always 2 behind N, and we get from that that A is equal to N minus 2. One of the nice ones to use is N squared. On this one, as I move N, you'll see that C zooms off the screen there, comes back again and moves back out. And that's really good for the pupils to see.
When this 1 goes up to 1, 0.
These pupils are trying to work out a different expression.
1 goes up to 5. But how would you put that into a sequence? It's every 1 N moves C moves 2.
C equals N.
Plus 2?
2 times N.
If they get stuck, they can reveal the answer.
Oh, right.
Okay, right.
C equals 2 times N plus 3. Oh, because if
2
you
times N
times
2 plus 3, yeah.
Yeah, because if you times 0 by 2, it will end up as 0, then you plus the 3.
Plus 3. So yeah, so
Yeah.
2 times N plus 3.
One of the very nice things that you can do with dynamic geometry software is look at various transformations. One very simple one is a reflection, and it's quite a nice interactive one that you can do with pupils. Very simply, just set up a reflection line, double click on it in this case to make it into a mirror line, and all we have to do then is reflect our shape over to this side. What I tend to do actually just to make it a little bit prettier, what we can see there as we move the points around, our shape moves with it. What's also quite nice is if we move the mirror line itself, and we can see what happens to the shape as it disappears off the screen there. It seems difficult to start with But you find adults get the hang of it quite quickly, and pupils are even quicker at picking it up.
And then
And don't you double click that?
Yeah, go double click the line. Transform.
Okay.
Reflect. And then it's come up on the other side.
Mr. Piggy's twin. Whee!
And just stretches
It's turning into Mr. Doggy.
Here we have a parallelogram. If I create one half of it, okay, so create the quadrilateral interior there and reflect it in the line that pupils often think is a line of symmetry, it's quite clear that it doesn't actually fit, so it's obviously not a line of symmetry. One of the nice things is as I move that point there, the parallelogram becomes a rectangle, and that's really good for linking together ideas about the key properties of parallelogram and the fact that a rectangle is actually a very special parallelogram.
Line.
These pupils are exploring the lines of symmetry in a rectangle.
Construct triangle interior. But if we reflect it, it goes off the
It
thing.
doesn't fit into the shape. So
But if we put the height up, it fits when it gets to a square. So that means a square is a special kind of rectangle.
in a rectangle, a
it's
diagonal line
a
is not a line
square
of
is
symmetry.
a special thing because it goes into it like that.
Much more simpler doing it this way than having to go through using a mirror or tracing peaks.
What we can do, another one we can look at is rotations. So if I rotate 40 degrees to start with, and then just join up my two end points there, I get an this is an isosceles triangle now. I could then rotate about my original point to see how many times that would fit around a point. This gets the idea that there are 360 degrees around a point. I'm just going to create the interior there. And pick this up, rotate it 40 degrees, and then just keep rotating. Obviously pupils, if they didn't know that there were 360 degrees around a point, they might start with something like 50 degrees, see if you could see if it would work with a triangle with 50 degrees, and obviously it wouldn't, it would overlap or not quite meet. But we've got there a shape that's created using rotations of 40 degree angles. So this obviously creates a nonagon. One of the benefits of using dynamic geometry software is that it's quite precise and quite accurate. With pupils, very often we have to do the pencil and paper constructions. However, it's more convincing using something like this, which is precise. A quite straightforward one to do is looking at the perpendicular bisector. I'm going to construct equal radius circles at each end of that line by selecting the 2 points and saying I want the circles to be this particular radius. Obviously they don't intersect at the moment, but as I move that radius there to become larger, I've now got intersecting circles. This relates to the pencil and paper method where your compass has to be open to more than halfway, otherwise it's not going to link the two circles together. I can then construct the intersections on those and then construct the line that goes through those points there. You can see, if I change the line here, you can see that I still have a perpendicular bisector, even though it might be a different length line or it might be a different position. One of the things that's really quite easy to set up is circle theorems. Again, they're demonstrations rather than proofs, but they are quite nice demonstrations, and it is quite convincing for pupils to see that the angle subtended at the edge of a circle is half the angle subtended at the centre. So all I have to do is measure that angle there, measure the one at the centre, and we can see that that one's twice the original one. I can calculate it, I can go to calculate here and calculate twice the angle there, and it will give me the same answer. So we can see that twice the angle at the edge there is equal to the angle at the centre. Obviously with this one you can also demonstrate that as I move point B, nothing changes. Okay, so that's a very simple circle theorem and it's very easy to set up.
Calculate. Divide. Oh, 0.50.
It's also easy to prepare interactive demonstrations of popular maths concepts like Pythagoras.
What we can see with this Pythagoras example is that we have the two squares. The blue square there is cut to show a classic dissection of Pythagoras, and the pieces can be picked up and used to fill the square. And obviously pupils can come out to the board and do this themselves, or they might come out to the laptop and show how it might fill the square. And finally that one.
It might go down in that corner. Go there.
That could go there. Showing us that these squares can fit into that with that one, and it will always be like the same like that. There.
And this one we can change the length of the sides to show that it will always work. Most dynamic geometry software packages don't just deal with geometry, most are also graph plotting packages as well. So in this case I'm going to do 3x plus 2, and it does it for me straight away. I might then ask it to plot 3x minus 1, and we can see that the two lines are parallel. Obviously pupils can explore that very easily. It's a very nice, simple way in. We can look at quadratics very easily, so if on this one I ask it to plot a new function, and in this case I'm going to ask for 3x squared, and it will plot it very easily there. And then I can just ask it to plot a function such as the sine of x. So here I have the sine of x, and it's plotted there. I find dynamic geometry software is a really, really powerful tool. I use it so much in my lessons now.
Carol's Year 7 class are using a dynamic geometry package to plot straight-line graphs of functions and to explore their properties.
The next one we want on there is y equals 2x minus 2. So click on a space. Okay, fine. Okay, and there's your second one.
Y equals 2x plus 3. Y equals 4x plus 3. And y equals 3x plus 3. They're all they at the 3. They all meet at there.
Oh, right. The 3 is always the M1. So 2x plus 3, 4x plus 3, 3x plus 3, 5x plus 3 is always the M1. I wonder if it would do that if you did 2x plus 4.
That would come up there. Yeah, it meets at the 4. At the line, yeah, so that's where they meet on the y-axis.
So it depends on the last number. If it meets at the last number,
It's where it hits the y-axis.
What have you noticed so far then?
we've heard that it's the last number is whatever sides where on the y-axis where
Excellent.
it goes.
Lots of pupils noticed that the lines were parallel. They all noticed that they were crossing at the same intercept. I think they made more progress today in an hour than they would have done in an hour without the ICT.